Good evening. If you have activity 58 or if you've already completed the exam wrapper, you're welcome to turn that in as well. I saw a few people just got ahead of the game, maybe not on purpose. In regards to the exam wrapper, there are two announcements. When I originally wrote the answer key, or wrote the exam, sometimes what you do is you flip a question to like ask the opposite of the question. And so I left the incorrect key to answer. Your exams were graded properly, because that's done with a Scantron and something else. But the exam key that I posted online says the correct answer for question 11 is C, I think, and it's A. So if you wrote A for question 11, you got that right. You got credit for that. You don't write an exam wrapper for that. However, if you answered C for question 11, you got that wrong, and you need to do an exam. You are eligible to do an exam wrapper on that question. All right, exam wrappers are due Wednesday, start of class. And the other question was that there was a slight misgrading of question 24. There's multiple places where sig figs were graded, and I believe it was only the last part of that question where it asked you to actually find the new bowling point, where we didn't grade sig figs appropriately. If you missed sig figs in multiple places, we only took off once for the whole question. You only missed sig figs once in that question, and it was in this part, and you're sure you did the right sig figs. Circle that on your exam wrapper and let me know, because I'm going to go back through it anyway, and I can give you that half point back that you might have lost inappropriately to question 24. Any questions on that? All right, so we try to do our best when we grade, but it's really important, no matter if it's this class or other classes, go through and make sure that the grading was done appropriately and fairly. We make mistakes, we're human. So please hold us accountable if you find mistakes in the grading. All right, any other questions about the exam wrapper? I don't have any more office hours between now and Wednesday. Some of your best resources are going to be the people around you, but make sure that when you write your response in the exam wrapper, that it is clear to me that you now understand a question that you did not before. If it just seems like you wrote down an answer that you saw in someone else's, you didn't earn any credit back. That's not the point. The point is not to increase your grade. The point is to encourage you to learn the material now so that you stay on top of things so you don't get further behind as the semester goes on. That reflective practice is really important to me. If you do come by my office tomorrow or Wednesday, my door is open in either ETAS 125 or Science Lab 673. Feel free to drop in and ask me questions. I am happy to do that, but I don't have any specific office hours. Josh, you had a question?
Yes, I was confirming it. On the exam wrapper E, you did not give the correct answer to 4, number 4.
What was the answer to 4? What was the question?
Which of these 4 molecules would you predict to be the least water soluble?
And what is the correct answer to that?
I mean, you called me out, but I thought it was PCP.
Yes, that is correct. Is that not what's listed on the...
No.
Nothing's listed. That's what
Oh,
I was
there's
saying.
no correct answer listed.
Correct. That's what I was saying.
Does this mean that you guys are just shy to email me about this?
No,
or that
I'm
you
not.
haven't looked at it until today?
I'm
Oh,
not.
no, look at our discovery.
Some things we order in class, and it just...
I don't know what answer or number that letter that is, but you guys can figure it out. All right. Any other questions? Congratulations to those who ran this weekend and did not die. It was very cold. And who had other fun things to do. All right. Welcome to an exam question. Go ahead and talk to your neighbor for a minute. Try to figure out whether this person needs to go to the hospital or not. At least figure out what steps we might start asking in order to answer this type of question.
So this is for the normal. This is the graph is for the normal. No, like I'm trying to. I don't know. There's only one.
definitely got that.
Stat. What's the most? Wait, yeah. I just
Well, they say it's probably asking us to see what the rate that they can see this. Because this is just a type of sample. This is just the grade to 25. That's the sample. So then we're going to determine what I'm assuming is the
So it doesn't matter. It's what they say. One half basically would be offset. But it is, we gotta do one half, one half.
sorry. Okay, because that's why I have to ask for the 15th because and I have to make sure I'm really something about 16th. I'll be gone from the 16th to the 18th.
Yeah, it doesn't travel that far. 10 hours.
So I'm only missing Wednesday. It's on Tuesday, and I miss Wednesday and Thursday. Lab what?
It's not this week, it's the next week.
Don't scare me. I thought yeah, April 16th and 18th, which I'll be gone that Wednesday, but don't do that.
Bad advice.
Here's 1 hour.
They have to be in Georgia on the 18th. There's only 3 hours drive from Nashville to Norton, so I know so what happens is my first impression is yeah, I'm down. And then before you go to Nashville, still more. Maybe.
All right. I've heard a number of different things. One of them is that she's effed. Others that we're not quite sure where to start, what to do. All right, so big picture. Can someone explain what happened?
She took the wrong medicine.
Okay, she took the wrong medicine. Is that the problem?
No.
Or
Her body isn't able to eliminate that in the amount of time that it can kill her.
her body may not be able to eliminate that drug in the proper amount of time. How do we know? Do we have any tools that let us figure out whether she's effed or not?
We have a figure.
Ruby?
Call anyways.
So I converted the 7.64.
Don't worry about that too much, about the numbers. What tools do we have available to us?
So the graph is showing that the half-life isn't constant. Does that have anything to do with it?
That is one of the approaches we might be able to have. Why would that be relevant?
It takes like the showers, I think, to go from one half of what this graph starts with to. I might not tell all of it,
Okay, so let's go higher picture. What basic tools do we have available to answer that question? Will her body be able to handle this or not? Kalia?
Well, we have a sample of, well, figure 1, the graph is showing just somebody who took what's considered, I'm assuming, like a normal dosage. And at the bottom, you can see that it doesn't actually all, if you look at the end of the time, it doesn't actually all leave the body.
In the time that we have there, true.
Right. So if,
So let's zoom out though, further, bigger picture, Colin.
So with the graph, we can define what T1 half is. And so with that, we know the approximate.
Zoom out bigger than just today.
Say what?
So the homework for today I know is T1 half. That is one way that one tool that we might be able to use, but even bigger than that, because that's a subsection of a bigger component of this class. Logan?
It shows that, like, if you read just like the top portion, it says that in that graph it's only 25 milligrams, but it said that she took 500 milligrams. That's like a drastic difference. And if we're taking 25 milligrams at the peak was like 175 on the mean plasma concentration, you could think that'd be 500. You can use like proportion to find out like how much greater that is.
Sometimes that works, but it also depends on blood volume and a whole bunch of other things. So I've actually given you what her peak plasma concentration is, but I heard someone over here say what it is I was looking for. What is it we're looking, this is the simplest version of the tool that we're looking to use. Say again?
integrated rate laws.
Integrated rate laws allow us to calculate, if we know the initial concentration, how long until we get below a certain threshold. What is the time, right? If we knew K, could you guys solve for that? There might be different units, right? We might have to convert from nano to micro and back and forth, that kind of thing. But big picture, this is a question of, if we understand the kinetics of this reaction, we can then figure out if this person is in serious trouble or not, and we can give them advice. So, how does this relate to half-life? Half-life is a very, very, very specific time point in concentration versus time. What time point is that specifically? So maybe isotopes may not be. So can you say that more generically?
When half of something.
When half of it's gone. If it's radioactivity, it's half when the radioactivity is gone. If it's concentration, half the concentration is left. And there's a definition in this activity that hopefully most of you have done. The half-life of a reaction, T1 half, is the time that it takes for the concentration of a single reactant to reach 1/2 of its original value. Why is that relevant to this question? What could that help us do? Ruby touched on it earlier. We hear from someone who says people have spoken. Bria?
If you know, like, the half-life of the medicine that she took, you could find how many half-lives it would take for her to, like, for the blood to go down.
Okay. We could look it up, but if we only had this data, what would half-life help us do? Are there any trends with half-lives and rate orders? What about first order? What's the trend with first order and half-life? Say it again, Kayla? Okay, so no matter what our initial concentration is, the half-life doesn't change. So let's take a look at this. Talk to your neighbor, try to decide, is this a first order metabolism? Does a drug go away according to first order kinetics? Try to decide if this is first order or not, based on half-life. So 15 more seconds. I want you to draw a conclusion. Is this first order or not? That is your question, based on half-lives. All right, I want you to show on your hand what order you think that the metabolism of this drug is. Is it 0 order, first order, or second order? I see a lot of 2s. Can I have someone try to give me an idea of why that might be? Angel, you willing to share your group's discussion?
We just think that the slope is too steep
Okay.
to be a first order.
So that actually plays into it. Can anyone elaborate on that and maybe relate it to half-lives? What is that, Mohammed?
I don't want to say it.
I don't want to be wrong.
I don't want to be wrong.
Okay.
Yeah.
I love it when people are willing to be wrong, but I'll let you pass. Echo, thoughts?
Is it because it's 1 over the concentration? With that, and then you've got like half.
So the integrated rate law means that 1 over these concentration points is a linear graph if it's second order, but this isn't 1 over concentration, right? This is concentration versus time. Awesome?
Isn't half-life for a first order, like, consistent?
Okay, so let's take a look.
Like, as
Where-
it has, basically the time is consistent for how long it has? Whereas
Exactly.
With the second order, it's going to be exponential.
So let's take a look. How do we know, is this 0 order, yes or no?
No.
Why do we know that?
It's not linear.
If the concentration, the rate of change of concentration was constant, if concentration versus time was a straight line, it's 0 order. Alcohol metabolism is actually 0 order, with approximations, but for the most part, that is. Hence, 1 drink per hour, right? That very different for different people, but if you use that approximation, that's the rate of metabolism, right? So this one, what's the initial concentration? Can anyone approximate the initial concentration of this drug? 175? Is it not 0? Are we looking at the kinetics? Are we looking at the kinetics from here? All right. I have a lot of students who, when they try to do this, use this as the first data point to try to do kinetics. Let's not do that. We're talking about not the absorption, we're talking about the elimination of this drug. So let's use some common sense as well as some number crunching. Let's use both of those. All right, so our initial concentration is up there about 175 nanograms per mil. So what's half of that? Anyone smart on the draw? Quick on the draw with numbers. Just under 90, right?
Yeah.
87, so that's about there. So how long did it take to get from the peak concentration to that? Any guesses? I would almost say, 3 hours? Because it's the change in time from the peak to that. Right? We're not talking about how long since it started taking the drug. We're talking about what is the metabolism. So I don't know. Let's say 3.5 hours. What about the second half-life? How long is the second half-life? Which means going to half of 87.5, which is what? 43.75. So that's what there? How long does that take? How long does it take? What's the change in time? Maybe 5 or 6 hours?
3.5.
What about the next half-life? 22-ish? 21 point something?
21.8.
How long did that take? Okay. Is this first order? No. No, by definition, if it is first order, each half-life will be the exact same amount of time. And the activity you guys just turned in, activity 58, if you have not yet done it, model 2 goes into that. It has you look at a graph where it's 130 seconds, goes to half, goes to half, goes to half, goes to half, which means, like Angel was talking about, you're going to have more of a swooped graph because it is more exponential, the relationship between the rate and time. Change in rate and change in time. All right? So if we know it's second order, then could you answer this question? All right, we're going to come back to that a little bit later on in class. But what I want to do is talk about why it is that second order does not have a consistent half-life. First order does, and zero order does not either. All right? So we're going to leave you hanging on this for a little while. So I guess we'll answer a really simple question. Checkpoint. Click your questions open before we move on. Talk to your neighbor. Check with everyone around you. Make sure that you have a similar agreement and justification for why. A couple more seconds. Modify your answer if you changed. All right, closing up. All right, can I have a new voice to share how you would answer this question? Thanks, Shanidra.
I said false because it's not a first order reaction.
Great. If it's a first order reaction, first order reactant being consumed, we know that half-lives are consistent. We know that this is not first order. We just checked that. The half-lives keep increasing as time goes on. Hence, it is a second order because the only options I was giving you were 0, 1, and 2. Very nicely answered. You look a little stressed. All right. So our learning objectives for today, or mine for you, are a lot of it around half-lives. So to predict the time at which half the original concentration is reached, aka the half-life, I want you to be able to derive the half-life equations and not try cramming more information in your heads and memorizing them. What are the trends of concentration versus time for 0, first, and second order? We've been working on that for a week and a half now, so I'm hoping you're getting the hang of it, and half-life should help. So if we look at a concentration versus time graph, I want you to do what we did in that first page and use half-life to determine whether it's 0, first, or second order. Multiple ways to solve the same problem. The more tools you have, the quicker you're going to be able to solve a problem. And then what was also built into that first one was using real data to determine the rate order of elimination of the drug, and then from that decide whether or not a patient is in trouble and should seek medical attention from that. All right? That's actually what the second page is that I handed out to you guys today. This is a critical thinking application that I developed of this type of problem where you have a whole bunch of information. You have to see what's relevant and irrelevant and use that to make decisions. So if you're ever thinking of going to field of medicine, this is like a very, very, very small version of what you might actually come in contact with. It's not going to be as simple as, here's a question, what's the answer? Right? You're going to have to sort through a lot of information, so I like to try to kind of throw some extra information in there and see how you feel with filtering some of that. So that is going to be an additional piece of material that is not part of class, but a thing to practice with. If you can work through that on your own, ask questions to others, it'll give you an idea of how you're doing with the concepts and how you're putting it together with a bigger picture. All right. Let's answer some questions for first order, and we have some graphs that support that. You're welcome to use the graph or other knowledge to answer these questions. Couple more seconds. Check with the people around you, see if you guys agree. A couple seconds. All right, can I hear from a new group? Can I hear from Kayla, Matt, or Jason, one of you guys?
I just got here.
We said it stays the same because it's first order.
Okay, and does the graph support that? Was that it? Did you give an answer, Matt?
Nope. I think it does because every time it goes down, it's just divided by 2, so it stays constant.
Okay, so let's be really clear and articulate in our wordage. As the concentration goes down by a factor of 2,
yes.
Starts at 0.20 molar, goes down to 0.10 molar. How much time does that take?
7 seconds.
In this graph, that is 7 seconds. What happens in the next 7 seconds? Concentration goes down to half of what it was there. And then the next 7 seconds, it goes down to half again at 0.025. And then it would go down by the same amount each time. All right, this visual is really helpful. If we have a graph, remember in the very beginning of the semester, not beginning of the semester, beginning of last week maybe, I said if it's this graph, concentration versus time, it's really easy to say it's zero order because the rate of the reaction doesn't change. But if the graph is like that, and there's a curvature to concentration versus time, you can't really say whether it's first or second order. But now you can. So now you literally don't need to do any calculations. You can literally start at the beginning and say, okay, here's the initial concentration, here's half of that. How long did that take? Well, how long did it take to go to half of that concentration? And then look again, half of that concentration. Does that half-life stay the same, yes or no? Then we know if it's first order or not.
Great.
It's a cheat. It's one of the many tools that you guys have to answer the question of what order it is. And then to ask a question that someone asked on Saturday during supplemental instruction, why do we care? Why do we want to know whether it's first order or second order or zero order? Why does it matter? Josh, would you like to answer that question?
I'll ask that. That's exactly what I asked you. Why do you care? Then you couldn't hear me, so I had to type it.
Right. So, did I heard you in the end? Do you have a good answer for why we care?
You don't know. No, you explained it, and it still came back a little fuzzy.
Okay.
I think for me, you said knowing each component of zero, first, and second order for specific drugs, it mattered. You were talking about the half-life, and then you went into radioactivity, and I was like, oh, okay.
Okay, so let's have some people build off of how that all ties together. Avery?
Wouldn't it matter in like the instance of what we were just looking at in terms of medicine? Because when you're considering drugs within our bodies and what the half-lives would be to see if it's dangerous level or not, like.
So if you try to answer that very first question that we did today, you had an integrated rate law. The integrated rate law would allow you to say, well, how does the concentration change with time? Does it change according to the natural log of concentration, or does it change as a function of the inverse of concentration? Those end up with two very, very different calculations of how long it would take for that drug to get out of our body. So once we know it's first order, or once we know it's second order, then we have a lot more equations available for ways of describing the relationship between concentration and time. And so we're much more accurate in our ability to make predictions about how that concentration changes with time, or how the rate changes with initial concentration. A lot of those different things all fit together. So let's take a look at how we might describe this relationship here. And I think I've been suggested to make selections so we know what we're doing over time. Here's another example, right, where we have half of the concentration. What's the half-life for this substance, this reaction? What's the half-life for this reaction? 1 second, right? Then it goes from 16 to 8 over 1 second, goes from 8 to 4, 1 second. So it has a very similar shape for all the first order reactions. And then let's talk about not adding more equations to our mental space. If it is first order, we know that there's a relationship that exists between, let me draw it up here instead. We know that concentration versus time is not linear. So how do we get that data to look linear and to be more predictable? If we plot the natural log of the concentration versus time, are you guys okay with, we keep on changing around the letter that represents a reactant? Sometimes it's R, sometimes it's A, sometimes it's M, sometimes it's actually the reactant. We use generic letters a lot. Hopefully that doesn't throw you off too bad. So if we have a first order graph, we can plot the natural log of each of those points versus time. What is the y-intercept of that graph?
Okay.
Is it the initial concentration? ln of the initial concentration plus b. Right? What is our x value? What is x time? What is our y value at any point in this graph? And then our slope is k, but because we know that this decreases with time, and we know that k is always positive, then the slope is actually negative k. So you don't need to memorize this equation or any of the other integrated rate law equations, and I'm going to show you how you don't need to memorize the half-life equation either. So if we're talking about half-life, can someone describe why this statement is true for half-life? The statement that's underlined. Tyler, you want to give it a try? Humphrey? Okay, maybe take a little deeper of an explanation of that. Okay, so at a specific time, when we've gotten to half of the initial, that's defined as half-life. Any question with that? So this is our definition of half-life. And we can take this equation, and for specifically the half-life time point, remember that's only one specific time point in a, you can use this for any time, but if we're looking just for the half-life, then we can rearrange this equation where we have a sub t be half of the initial. So if we do that, I think this is all written out here. There's two different equations that we can use. We can either use this guy or the straight line form. Let's do the straight line form. So on the left side, we have natural log of you okay with that on the left side? Sorry, I should do the same brackets. Anyone have questions so far on what I'm doing? Yeah, Colin? Thank you. It is not for all times. It's really important that you put t1/2 there because it's only for one time point. Okay, so then how do we rearrange that equation to try to isolate t1/2? Kalia?
You can use subtract natural log of the initial from both sides, and then use the log, logs, you can divide, or write out the ratio
So then you're saying that the left side of the equation, using the rule of logs, is natural log of the initial concentration over 2 divided by Is everyone 100% comfortable with logs? If you say no, did you watch any of the videos I sent or find your own resources? All right, so from a historic perspective, I can literally tell you that you will, maybe that's a little bit strong. This overly strong statement is you will not get an A in this class unless you understand logs. It actually might stretch further than that, but logs are the underpinning to the calculations for this semester. So I'm not playing when I say that you really need to understand logs to succeed in the semester. It applies to kinetics, it applies to equilibrium, it applies to thermodynamics, and all of our calculations will be log-based. So you are going to be so much better off if you can understand the math. So please believe me and take the time and go brush up on how to rearrange logs and what they mean. There's 4 resources I sent. Even if you just watch those, it'll take 45 minutes and it'll drastically impact your grade this semester. If you don't believe me, you can ask the supplemental instructors. It is the biggest tripping point for Gen Chem 2, without a doubt. All right, so if you believe me that we have natural log of initial over 2 divided by initial, what happens to that fraction? Our initials cancel out. So then that simplifies to natural log of, let's say, 1/2. It was 1 over 2, right? It's half of the initial is what we had. And that equals negative KT. Once again, rule of logs, if we invert the sign of a log, what happens to the fraction within it? Flips over. So I'm going to go up here. So ln of 2 equals positive KT. And then, this is T1/2, right? How do we isolate T1/2? Divided by K, and then we can erase it from the right side. All right. Is that easier than memorizing it? It looks like a lot of you guys are going to say no. The other way is if you use this equation here, and you put a negative sign and flip that fraction, then you can do the same thing with initial being half. So half of initial and initial, you'll come out with the exact same thing.
So can we use that equation?
Yes, you can. You can use either of those equations. You can double check using any equation. Point, why does it matter? How does half-life change in relation to concentration, the initial concentration? Do you guys notice that in the equation that we just came up with, how concentration isn't part of that equation at all? Does not exist as part of that equation. That justifies the fact that for first-order reactions, half-life is set. Radioactivity, we said, is always first order. No matter how much radioactivity we start with, it's always going to be the same amount of time for it to go to half the initial concentration. Half-life is always the same, regardless of initial concentration. So I think all that's kind of written out here. You can do this in the fraction format, in which case it all falls out as well. I'll put this up there so you guys can go look through how I did it for that one as well later. Let's talk about zero order. What are the trends for zero order and half-life? Check with your neighbor. Justify why as articulate as you can. But you're still gonna say what? All right, I want an articulate justification. These? Someone like to share their thoughts? Lindsay, thank you for volunteering. What did your group discuss?
Well, from the graph, we can tell that it decreases.
What decreases as what changes?
That half-life decreases as the concentration decreases.
Fantastic. So, amount of time it takes to go from initial to half of that initial concentration, second time, this amount of time versus this amount of time. All right. Is that going to be different depending on the slope of that graph?
Yeah.
Are we ever going to have a time at which the half-lives don't get smaller? That relationship is always going to hold true. So I could give an exam question. Half-life with this initial concentration is this. Half-life with this initial concentration is this. Based on those two pieces of information, you should be able to say, well, there's lower concentration, it's a lower half-life, it's zero order. You don't need any other information. That's it. Because that trend always holds true. If you're ever questioning it, then you can just draw out a zero order and say, okay, well, I can't really remember. I don't remember. Beginning of every semester, I literally draw a line and I say, okay, here's one half-life, here's the second, here's the third. Okay, it decreases as concentration goes down. Do you have a question?
Can you repeat the way, like if we didn't have the graph, would we repeat that question?
So if I told you at this concentration, here's the half-life, at this concentration, here's the half-life.
Okay.
If the two half-lives are the same, concentrations are different, what order is that? First order. If the half-life at the lower concentration is smaller than the half-life at the higher concentration, what order is that? And what do you think it's going to be for second order? The opposite. So we'll see that in a second here. All right. So if we go through and we do the same equation, right? This the equation for this line for concentration versus time, the integrated rate law for zero order, if you will. To derive the half-life equation, what are we going to do with this equation here? We're going to write T1/2, and then what else are we going to do? Say again? So we put concentration at time t being half of the initial concentration. And if we do that, right, divide initial divided by 2, we rearrange that. We have initial minus half of the initial. It's half of the initial, right? 1 minus half is half. And then we divide that by k. Well, there was already a 2 there. So we divide both sides by k to isolate T1/2. So what does that mean? As concentration goes down, what happens to half-life mathematically based off of that equation? Why does it go down, Love?
Because as your concentration increases, as your concentration increases, you're still dividing it by 2k, so it's going down at double the time, or like decreasing at 2 times each time.
Well, I would say it's proportional, right? Because the initial concentration is in the numerator, that if we're starting with 1,000 grams of something versus 50 grams of it, that's going to be a different initial amount of concentration, and the half-life is going to change proportionate to how much we have or what the concentration is. Second order, what are we going to say? You have 15 seconds to answer this one. I don't think we need much more time.
Yeah.
All right, closing out. Can I have a new voice to help articulate your answer to this question? Carol.
The half-life increases
as the concentration decreases.
Fantastic. So we can see, just looking at that big swoop, we have a shorter half-life. As the concentration gets lower, the opposite effect has opposite effect on half-life. Half-life goes bigger as concentration goes down. Once again, we can derive that using the integrated rate law for a second-order reaction. We're going to replace concentration at time t with half of the initial concentration, and that is T1/2 now. So hopefully you can see on the right, if we move the 0.5 is the same thing as 2/1. 2/1. So this is just rewritten from here. So what does this fraction end up being? 1 over the initial. You guys okay with that? So 1 over initial concentration is on the right side. On the left side is KT. Once again, I would really love it if you guys tried not to memorize these equations, but to be comfortable deriving it just by looking at the integrated rate law, plugging in half of the initial for your concentration you're looking for. So as the concentration goes down, what happens to T1/2 mathematically? Anthony?
It's going to increase.
Why is it going to increase? Mathematically, why does T1/2 increase when concentration goes down, now that we know that relationship? Say again?
The fraction becomes closer to a whole number.
Okay, so as the numerator gets smaller, or sorry, the denominator gets smaller, the fraction gets bigger. Great. All right. I'm trying to remember if this is the next thing I have. It is not. So if we ever look at radioactivity, you're never going to see, based on the initial concentration, the half-life is. Why is that? Why are we just given the half-life and the radioisotope? Colin?
Because the concentration doesn't affect half-life, the first order reaction.
And we know the radioactivity is first order. Great. So let's answer a question based off of radioactivity. Question number 10.
So I made a great mistake. I didn't even know that I heard you talk about it. So instead of studying my emotion, oh, that's right.
Well, she was kind of stupid.
Well, I mean, I read the book, so I knew what happened in the first season. But I was sitting there, I was just like, yeah, that's how I was starting to that character, like the characters, the books, and the setting that I was like, okay. But Braden keeps saying, so we need to go back in time or way. So and they talk about that was so funny. About murder and drugs. It makes you feel any better? Right, we have to really so at first I wanted to take and she said no, she didn't really school. Like to see, but anyways, whatever. And so I was afraid and I was like, damn, I want to go because anyways, if she's a hardcore fan, she would go. Anyways, so I told Brayden, and Brayden said, oh, I'll go with you if nobody else does. I said, no, you can't go. You don't like their music, so you didn't go. I'm like, no, it's fine. I'm asking. I don't want to be a burden because they're gonna be like, oh, that's your boyfriend. But best believe, I'm being horrible, but also like, that's what I want to make sure that.
That's
What do you mean?
All right. Can someone walk us through how we might solve a problem like this? Kayla, thank you for volunteering.
Hey.
You use the derived equation, which is T1 half equals natural log of 2 over K, and you're looking for K, so you have to rearrange that, so you must multiply by K.
Like that? I can write sometimes. What are the units of K? Are there any units in natural log of 2? Are there any units in the T1 half? Years. Time has a unit. All right, so our units for K are going to be inverse years. You could convert it to minutes, you could convert it to seconds. This might not be very useful, it depends on what your application is, but it might be appropriate. And then what is a numeric value for that? Can I have someone share? Kayla, what did you have for your number?
It was big, I don't know, it's like 121. Yeah.
I don't know that your parentheses might have been great.
But when I put parentheses, it was like 0.00 something.
Logan?
It's 1.21 times 10 to the negative 2. Yes.
How do we check it? Did anyone do it a different way than this, by the way? Could we use the integrated rate law, the full integrated rate law? Absolutely. We just plug in the initial concentration is 1 and the final concentration is half and figure out with our t that we know, 5.73 times 10 to the third years, that would be the exact same thing. It would give us the same k value. All right? So then, what can we do with that? Can you guys answer the next question now? So, is that the number that we got, 1.21?
Yes.
Yeah.
Okay.
Yeah.
So with that, how many years does it take for 90% of a sample to go away? Go ahead and take another couple of minutes to answer this question. Question number 11.
What's the first one, 9 times?
Okay, so I'm making up some numbers. The natural log of 18 is natural log of 8. Is an integer say I don't know what you said.
I'll say based on this, 6 minus 9 So you're putting in I'm making sure that I'm doing this right.
19,000 years something, right?
So the final the initial's 100, so initial's 100, final is 10. Okay.
I don't know that's right. I made some numbers up. That's what I heard.
So, no, 100 is the initial.
I'm still So question, sorry to bother you, but so we divide these outside block chains. Why is it so long?
Because that's where 90% is taken from.
Oh, okay.
The next level, that is.
And then by 0 plus this.
That is 0, so it's 0.
Oh, because it's can't. So you divide by
That, yeah, so that.
and then
This negative gives us negative.
Okay, I got a lot of numbers.
Around 19,000 something. Carbon dating.
We're not looking to, we already know, why would we do that? Why can't we just do
Who automatically went into plug and chug mode? Did that work?
Yes.
Okay, some of the people it did. How many people didn't find that worked so well? I saw a lot of people try to plug these numbers into the half-life equation. When does that equation work? When is the only time that equation works? When you're looking for half of the initial concentration. Is that what we're doing here? No. We're looking for when 90% is decomposed. All right, second part. I saw a lot of people plugging in 90%. Why is that going to run into problems?
That's saying you only decompose 10%.
If we have 90% in, that means 10% has decomposed. We're left with 90%. So you really have to read the question to make sure you're understanding, is it how much is used up or how much is left? So I know that your pre-lab quizzes showed you examples where it was then 1 minus 0.9. I don't want to do 1 minus. Think about what's left in the end. So how much is left in the end of this reaction? How much of the carbon-14 left? 10%. 10%. So let's use 10% and not 1 minus 0.9 because it just ends up being complicated. If it works for your brain, go ahead. That's fine. But just don't get it wrong. Don't get it mixed up. Because I might not follow what you're doing if you have 1 minuses. Okay? So which equation are we going to use? First order integrated rate law. We can either use this version or we can use, I don't know why this keeps popping. Problem is I made these slides a while ago. I don't like this form of the equation. Anyway. That's super confusing. Let's not do that. All right. So did anyone use the ln of the fraction form? Yes. So what do we do then? ln of 0.1 over 1.0 if we want to use that relative value, right? Equals minus kt. That works. So then what does this fraction become? Natural log of the percent remaining. That's going to be useful as far as saving time, recognizing that that's just the percentage remaining. And then what do we find for t? We know what our k is. We can plug that in there. What did you guys find for our time? Austin, what did you find? Wait, before you say that. What is a reasonable number here? I heard a lot of people say, this number doesn't make sense, which I love. What does a number have to be bigger than? Bigger than 0. Great. No, it has to be a positive number. That's important. Has to be bigger than the half-life because we have more than half of it gone. What else does it have to be bigger than? Why 2 times the half-life? Did you guys think through that?
Wait, what?
1 half-life, 50% used up. 2 half-lives, 75% used up, 25% left. What about 3 half-lives? 12.5% left. So it should be longer than 3 half-lives. What'd you get, Austin? 19,029. Sorry, there should be a 0 there. And units? Okay. And based off of sig figs, it's terrible. This is a bad question for sig figs because 90% only has 1 sig fig. My bad. All right. Thoughts? Matt?
I didn't use that equation. I just used the normal equation and then just rearranged it.
Great.
Still got the same answer.
Fantastic.
These ones confuse me, so I just used the original and algebraically.
Perfect. No. I'm not saying that this is the appropriate one to use. There are 2 versions of the same equation.
Yeah.
One is using a fraction, one is using them separated by each other. Did anyone get a different value? Do you know how you got a different value? Okay. So, say again?
Did 100 over 90.
So you used the positive kt, so it flips these, but then you did how much was, instead of how much has been used up, you said that 90% was remaining. So you would have got a time of like 800 years or something like that. And so hopefully logic kicks in and say, more than 50% of it's gone, so it's got to be more than a half-life, right? All right. So I want you to be able to utilize these and come to conclusions. All right, really quick question. Is this worth doing?
Yes.
How much time do we have left? No. What do we have to have in order to use carbon dating? Carbon. So I usually put this up there to like ask students to think about, can we carbon date these things? Which ones can we use it for?
You can't use it for millions of years, man. It's not.
All right, go ahead and click in your answer.
You gave it to me numeric.
That's okay, we'll put one.
Put 1, 2, 3, or 4, I guess.
It's more than one.
Just one of the answers. Why might you think it's more than one of the answers? Josh?
Because there's carbon and bone.
So there should be 2 answers, right?
No,
No. Why not?
because it's only relative up to not millions of years, just tens of thousands of years.
We just calculated how long until 90% of the carbon-14 is gone. That's 19,000 years. Think about how little is going to be left after 68 million years. So someone brought up something very interesting. In office hours, does radioactivity ever go away completely? No, not really. Right? It's always getting cut by half, by half, by half, by half. But at a certain point, you can't really register it anymore. You can't use it to back calculate the age of anything. And so usually we say after about 5 or 6 half-lives for carbon-14, it starts at such a low concentration that it's not really that useful. After, maybe I'll take that back. I'll say 10 half-lives. So after about 50,000 years, we can't really say how old something is based on radiocarbon dating. So then how do we know how old dinosaurs are?
There's other methods of dating.
There are other radioactive isotopes that have been around for a very long time and have a much slower half-life. All right.
Great.
So let's go back to our first question. And you guys will notice that on page 3, you have all the data to support the figure that you had on the first page. I have done some calculations and manipulations. I want you to figure out what the rate constant is for this drug, and then go one step further and figure out if this patient, if she needs to go to hospital or if she's going to be just fine. Support it with data. All right, take 3 minutes to at least set up this problem, and then we'll talk through it in about 5 minutes left of class.
0.0769172 divided by 35.
You said what? Oh, because of the time.
So to make sure we're doing this efficiently, what is the rate order for this reaction? Second, remember we determined that using half-lives.
What is the rate cost? What's it called? Okie dokie. Excuse me. Yes, but still, hold on.
You want your answers? One of the six. Okay, most important thing is, did you get a chance to figure out how to set up this problem? I'm not as worried about finding the right number yet. What is it that clued us off on how to start working through this problem? You say we start from the beginning? Say again?
So you look at your, since all the graphs are available, you found which one is linear, so you know the order right off the bat, so you know which.
True, if we didn't know the order already, but from the half-lives we also knew that it was second order, so this kind of confirms that. So then what do we do?
So we used the graph like we did last class. So we took we used the time from we used the natural log concentration using the chart of the 1 over the concentration, using the value for that was given for 36 seconds, and then the value given for 0.5 seconds.
What? What are you talking about?
You said on the table, the values for the 1 over T, or the 1 over concentration, for time at 36 and time at 0.5.
Oh, you're talking about hours. Okay. I was like, we don't have seconds. So you started at 36 hours. So you used this data point. And then which other data point did you use?
1 hour.
The 1 hour. Why did you not use a time point before 1 hour? The drug is still being absorbed up until an hour. So any elimination kinetics are irrelevant before that time. And then what you did is you found the slope between those 2 points, correct? And that is our rate constant. So did anyone take that number and then look at whether that patient should go to the hospital or not? Can we figure that out? What are the units of our rate constant here? What's the number? Logan, can you share your value with us?
It's like
2.031 times 10 to the negative third.
Units?
Hours, right? No.
So hours.
Oh, yeah.
Okay, we can't forget about the fact that first order, the units are concentration over time. Second order is per time. First order is per time. Second order is per concentration time. All right, if you're ever wondering about that, go back to our differentiated rate laws. Units on the left are always concentration per time. So the right side concentration squared. K has to be the right units in order to get it. The left side units to be the same as the right side units. So we're not going to have time for me in class to go through and show how to utilize that. Please do that before class on Wednesday. And what we're going to do on Wednesday is start off class with Happy Gilmore.
Yeah.
And then we're going to talk about how temperature and catalyst influence rate, which is what your pre-class quiz is about for Wednesday.